Since school is canceled for tomorrow, I wanted to go ahead and try to complete our lesson 4.2. There's a couple of things that I want to remind you from last Friday. The first one are these three formulas. The summation of I squared, and I cubed. These are formulas that by the time you finish homework, you should be extremely familiar with if you don't already have them memorized. So we're going to be using these indefinitely for this section. The other thing that I wanted to remind you is something that we touched at the very end of class. We were talking specifically about why in all of our examples are we taking the limit as n approaches infinity. I've showed you this example. If we were trying to find the area inside this circle and we were to use another shape, say a triangle, we could use an inscribed triangle, which is the smaller triangle. And if we did that with n being 6, meaning 6 triangles, we would recognize that the area of our 6 triangles would be too small compared to the area of our circle. We could also extend our triangle to the outside of our circle, and we would also recognize there that our area would be too large to represent the area of our circle. We then looked at an example where we took the number of triangles and we increased it to 12, and we were able to recognize that the more triangles there are, the closer we are to the actual area of the circle. This is why in all of the previous examples we always took the limit as n approached infinity. If there were an infinite number of triangles, we would not be close to the area of the circle, we would have the exact area of the circle. In this next example, we are just going to be using basic algebra, base times height, to be able to compute the area underneath this curve. Reminder that we have a calculus way of finding area and we have a pre-calculus way of finding area. The pre-calculus way, we would not be able to find the area underneath this curve. Okay, so calculus basically allows us to be able to find the area underneath something that's curved like this. And this is where integration actually takes place. So if we were to try to find the area underneath this curve the pre-calculus way, our only option really would be to break it up into a certain number of rectangles and basically do base times height, or length times width. Add the sum of those 5 rectangles together, and we know we would be less than, but we would be close to the actual area. Okay, we're going to actually do that exact thing in this next slide. So basically what we need to look at is what is the base and what is the height of each one of these rectangles. Okay, if you can look at the interval here, each of these rectangles is broken up by 2/5 basically. So it's 2/5, it's 4/5, 6/5, so on and so forth. So we know that the base is always going to be 2/5. So if you look here at the way this is written, we have L sub 1 times 2/5 plus L sub 2 times 2/5 plus ... plus L sub 5 times 2/5. So the L1, L2, and L5 is going to represent the height. Now, we used what's called right endpoints. And what that means is that the right endpoint of our rectangle, such as this point right here, here, and here, is the point that is actually on our curved line. If we use the left endpoint, okay, which would be right here, and then our rectangle would be coming on the outside, we would be able to use that type of rectangle as well. However, obviously that area would be too large for the area underneath the curve, just like the right endpoint ends up being too small to find the actual area. But here we go. Basically what we would do is take our base, which is 2/5, and we would multiply that by the height, which is our f of 2/5, f of 4/5, f of 6/5, so on and so forth. Okay, and as you can see, that's basically what we've done here. Okay, keep in mind our function is right here. It is negative x squared plus 5. So when we put 2/5 in, you're putting 2/5 into the x, squaring it, multiplying it by -1, and adding 5. When you do that to this figure and you add this in 5 times, you should get 6.48. We really need to look at another way of writing this calculation. Think about if we were to use n equals 50. Okay, in that case, if we wanted to use 50 rectangles, it would not be a very good choice to just add up 50 of those rectangles. So there is a way to write this faster to be able to compute it a lot better. And we're going to do that with this same exact example of f of x is equal to negative x squared plus 5. Okay. The first thing that you need to recognize is that we are doing a summation. We are adding up the 5 rectangles. Okay, so we are going to have our I going from 1 to 5, 5 being the number of rectangles that we have. And all we have to do is we have to multiply by our height and our base. Okay, now the height, you might be asking, why do we have I in there? Okay, previously you saw the f of 2/5 times 2/5, f of 4/5, so on and so forth. But what the I does is it helps us to have that counting mechanism to get to the next one. So for example, I is going to start at 1. When I do that, I would have f of 2/5. If I is 2, then I'm going to have f of 4/5 times 2/5. Okay, and because of this summation, all of this is being added together. Alright, so let's go through and actually solve this. What you are doing is you are taking this 2/5 I and you are substituting it into your equation for your x. Okay, so we still have the summation as I goes from 1 to 5. And we have the function of negative, okay, x is our 2/5 I squared plus 5. And that is being multiplied by 2/5. Okay, now I'm going to say it again just to make sure you have it. This is our base of our rectangle times our height. Okay, and what the I is doing is helping us to get to all 5 of those rectangles. Now it's just simple algebra, just like we did in examples on Friday. So here I'm going to go ahead and I'm going to square this. So I still have the summation as I goes from 1 to 5. Okay, 2 squared is 4, 5 squared is 25. It's still going to stay negative since the negative sign was outside, plus 5 times 2/5. Okay, now we're just going to go through and we're going to distribute the 2/5 in. So we still have the summation as I goes from 1 to 5. I'm going to multiply the 2 by the 4 and get negative 8. 5 times 25 is 125, I squared, plus, and now we're going to distribute the 2/5 into the 5, and we just get a simple 2. Now we can go through and actually separate our summation. And keep in mind, the whole goal to this is to get down to I squared, or I cubed, or some constant. So this negative 8 over 125, I want to make sure that I pull that out in front of the summation. So that's what I have done here in this next step. It's negative 8 over 125, summation as I goes from 1 to 5, and I'm left with the I squared. Plus, I can separate these into 2 separate summations. So now I have the summation as I goes from 1 to 5 of just the 2. Okay, when we continue on through here, I still have my negative 8 over 125 on the outside, but now I can replace this summation, I going from 1 to 5, I squared, okay, with my formula in here. Just keep in mind that we do know that I is going not from 1 to n, but it's going to 5. So in this case, n is going to be equal to 5, and I'll go through that substitution in the next step. I just wanted to get that formula down so you knew where that was coming from. Plus, summation, anytime you have a constant here without an I, you can simply multiply your upper bound times the constant as long as your lower bound starts at 1. If your lower bound does not start at 1, you can't do that. But in this example, I can take the 5 times 2. Okay. Now, in this next step, this is where I'm substituting in my n equals 5. So I have negative 8 over 125, and each one of these I'm just substituting in a 5. So here we have 5, n plus 1, 5 plus 1 is 6, 2 times 5 is 10, plus 1 is 11, over 6 plus 10. Okay, obviously the 6's cancel. You can go through that with your calculator, and you should get the exact same answer as we got before by doing the area of the 5 rectangles separately and get the 6.48.